Let me ring the bell. More people inside. Need more people inside. So. More people inside, right?
Yeah. I think.
Okay. That's great. That's great. Okay. Okay. Okay, I think we can start. So it's my great pleasure to introduce Dr. Sandro Tacchella. So Sandro is the new assistant professor at the Cavendish. He did his PhD at the Swiss Federal Institute of Technology in Zurich. Then he moved to Cambridge, but not our Cambridge, the one in US, as a CFA fellow between 2017 and 2020, right? And then he moved for a year in Korea at UNIST as an assistant professor, and is now an assistant professor at the Cavendish. And he's going to talk about spatially and temporally resolving the wondrous lives of galaxies. Sandro.
Okay, can you hear me? Yes? Okay, yeah, well, Nicola, thank you very much for the kind introduction. So I'm, of course, very honored to start this position here at Cambridge, and I'm very excited to, meet you all. So I stay now in office, colleague K29. So, feel free anytime to pass by. I'm very happy to chat with any of you. So in today's presentation, I will talk about the lives of galaxies, and I will do so by going over several different projects that have been, encountered in my life as a researcher. And so I might skip over some technical details, but if you are interested, I'm very happy to talk with you about them also after the talk or anytime in my office. So when we think about galaxies, we automatically think about cosmology. And the last 2 years, we have, of course, gained a lot of insight from different cosmological probes, including the cosmic microwave background shown here on the left. This is an image from the Planck satellite. And so from these cosmological probes, we understand now that we live in a universe today where the energy budget is really dominated by dark energy. The matter itself is dominated by dark matter, and the matter we all know about, the ordinary matter or the baryons, is only making about 5% of this whole energy budget today. And despite having very little clue about what that dark energy is, and also a little bit, only a little bit knowledge about what dark matter could be, we still think that we have a good understanding of the initial conditions for galaxy evolution. And this is because if we assume now that our universe, is just made out of dark matter, let's assume cold dark matter, you are actually able to very well propagate the initial conditions from the cosmic microwave background to redshift 0. So we can do this by, with n-body simulations, solving the, gravity basically. And you can see we can construct maps such as those where we, show the large-scale distribution of the dark matter. You can see the beautiful filaments and also cores of galaxy clusters. And it has been shown now that this large-scale distribution of dark matter actually is very consistent with what we see when we look at the large-scale distribution of galaxies. This is from redshift surveys. One of the first ones was taken by the CFA. So my office neighbor at Harvard was Margaret Geller, and she did the CFA redshift survey. And it's it's clear that, overall, lambda CDM is able to also reproduce the large-scale structure in the universe. Now, when we go to, to more details and compare, for example, the galaxy stellar mass function with the dark matter halo mass function, now this is now renormalized by the cosmic baryon fraction, you can see that there are some differences. In particular, at low masses, as well as at high masses, there seems to be somehow an inefficiency for star formation. So you need to somehow have baryonic physics playing an important role in how galaxies grow, so that there is a difference between the dark matter halo mass function and the galaxy mass function. You can see this also when you look at the color distribution of galaxies. So this is showing you the U minus R color. This is dust corrected. So what you're looking at is mostly age of the stars as a function of the stellar mass. You can see that when you go to the most massive systems that they are all actually quite red. So this is what we call the red sequence. So these are objects that have very little star formation. And down here we have the star-forming galaxies, the blue cloud. And again, this is counterintuitive if you live in a cold dark matter universe, because there you live, you think that the largest objects are the ones that formed most recently. And so in order to inverse this age trend, you need to have these objects actually stopping their stars quite early on in the universe. So they form a lot of stars and then they cease their star formation, or what we call this also is quenching. They have to quench their star formation. Now, thinking a bit more about the baryonic physics, it's of course important to think about scales. Okay, so I showed you already the large scale, cosmic web here. This is on gigaparsec scale. Then galaxies live in dark matter halos. They're typically of, a few megaparsecs in size. And then galaxies themselves are really the tiny entities in the very centers of these dark matter halos with sizes of a few kiloparsecs. Now, thinking about galaxies, of course, the large-scale distribution of the matter is important. Whether a galaxy lives in a cluster or in the field has very important consequences. But when we look at galaxies themselves, they have also a lot of beauty in them, right? We can see that they have, their dense cores, typically what we call a spheroid or a bulge, and then they have the spiral arms. And the star formation itself takes place actually in quite tiny entities in giant molecular clouds that are only a few parsecs in size. We also think that most galaxies harbor a supermassive black hole in their core. And these black holes, although tiny, they have very important consequences, as you will see, for the evolution of galaxies as well. And so, for me at least, it's very interesting to study galaxies because they connect a wide range of different physical processes, ranging from small scales, thinking about black hole feedback, black hole formation, star formation, all up to the large-scale structure of the universe. So despite galaxies being very complex, where a lot of physics is going on, they still obey scaling laws, right? So here I show an example of the star-forming main sequence. So this is a relation between the star formation rate of a galaxy and its stellar mass. And so what I show you here is the specific star formation rate. This is the star formation rate divided by the stellar mass as a function of the stellar mass. And what you can see in this figure, maybe it's a bit difficult to make out, but you can see that there is the star-forming main sequence, this relation for star-forming galaxies at all cosmic times, going from redshift 0 today all up to redshift 2, which is about 10 gigayears ago. And it has been measured that this scaling law has roughly a width of about the factor of 2, so about 0.3 dex. So it's quite narrow. What you also can see is that there are these galaxies below the star-forming main sequence, right? And they seem to get more, higher in number with time, with cosmic time. And you can see that here, there are a lot of objects down here that seems to be like a second sequence. Now, this is similar to what we have seen with the red sequence before, but I would caution here that this is not really a sequence in itself. These are mostly upper limits because it's very difficult to measure star formation rates or specific star formation rates below 10 to the minus 12. And so you can think of this probably kind of an extended strip where a lot of objects are sitting actually much lower values. So moving forward now, there is also an interesting link between the star formation of galaxies and the overall structure of galaxies, right? The morphology in galaxies. So galaxies that are star forming today are looking something like this, right? They are beautiful disk galaxies, what you also call late-type galaxies. And then galaxies that are down here, quiescent, they seem to look much more boring. But however, when you look at their kinematics, they're actually also quite interesting, right? There is actually a strong gradient where we have at the low mass end of the quiescent sequence having mostly fast rotators. So these galaxies are still dominated by ordered rotation, but then galaxies at the more massive end is what we call slow rotators. Those galaxies are typically dominated by random motion. Now, when we look at today's universe, right, we would say, oh, okay, how do these galaxies evolve into those galaxies, right? How do you transform the, first of all, how do you quench the star formation, switch off the star formation, but also how do you change the morphology of galaxies? I think this is not the right way to look into this, because when we think about how much star formation is actually going on today in those objects, it's very little. If you would move now this point here, to the right, and you would, let's say, wait for the Hubble time, so for the age of the universe, which is roughly 14 giga-year, this point would only move by about a factor of 2. Okay, so it would move about here. So it's very difficult to explain how those galaxies here, roughly Milky Way mass or slightly below that, transform into these massive galaxies. And so the idea is actually to not look into today, if you want to understand the progenitors of those objects, you actually need to go back in time, because the progenitors live somewhere there. And so you will hear me talking today a lot about Redshift 2, the key epoch, to understand the formation of a lot of the quiescent galaxies you see today. And so the last 10, 20 years have been very fruitful in measuring actually the overall galaxy population as a function of redshift. So here I show you the cosmic star formation rate density. So this is, you can see here, this is today, going back in time, look back time of 10 giga-years, redshift 2, and then go further back in time, all to the realization and cosmic dawn epochs. You can see there is this key epoch around cosmic noon where the cosmic star formation rate density peaked. And this is really where most of the stellar mass in the universe has formed. And so in the next few minutes, I will be talking about several different, different questions. I will start by trying to answer the question, when and how did galaxies form their bulge and disk components? I will move towards generally the understanding of how galaxies regulate their star formation and also in particular quench their star formation. And then towards the end, also a bit more outlooking towards the James Webb Space Telescope, talking more about when, why, and how did the first galaxies form. So let's start very simple, right? So we discussed already that the dark matter halos are building up with cosmic time. So you see, you start out with smaller halos, and with time, you're generating these larger dark matter halos. Now we can start with a very simple model where we just say the star formation rate is proportional to the accretion rate of gas, right? So this is maybe a first order assumption. And so we can express the star formation rate in a given dark matter halo at a given epoch just to be a star formation efficiency, the baryon fraction times the dark matter accretion rate. Okay, so it's basically the gas accretion rate here, and then you have some star formation efficiency, which you can tune, for example, to reproduce observations. And we used here the UV luminosity function redshift 4 because that is very well established. So here in this work, I've been focusing in particular at higher redshifts. So here I'm talking of redshift 4 and above. And again, just a side note, so this work here I have actually done here at the at the IoA when I was visiting back in 2012, my very first trip abroad. Okay, so how does such a very, very simple model do? What I want to highlight maybe is that this is really one of the most simplest models you can create, because you see even the star formation efficiency only depends on halo mass, right? It has no redshift dependence. Okay, it's just a halo mass that you calibrate once at one epoch, and you just assume it's fixed. And the result that we get from calibrating at redshift 4 looks something like this, right? It's basically the peak around 10 to the 11 solar masses in halo mass, which makes a lot of sense if you remember the figure which compares the halo mass function to the galaxy stellar mass function. So how does such a model reproduce the cosmic star formation rate density? And you can see it naturally does this very, very well. But you can see that it can explain this very strong increase in the cosmic star formation rate density with time, or down to lower redshifts. And so why is this the case? Well, if you think about the star formation efficiency peaking around 10 to the 11 solar masses, we can now think, okay, well, with this equation, right, what is the key here? Well, the key is the halo mass function. And the halo mass function from redshift 10, down to redshift 8, 6, 4, is moving into this regime here where the star formation efficiency actually peaks. So what you end up with is having more and more dark matter halos that are able to host galaxies that form stars efficiently. So this is the first part of the story. And the second part is, of course, this term here, that also the accretion rates of the more massive dark matter halos is higher. So you also have higher accretion rates. And so this combined effect leads to this strong increase in the cosmic star formation density at early times. As you can see, there are models that also would predict a flatter leveling off, right? Higher cosmic star formation intensity. And I would say that, at the moment, we really don't know. We have just no observations there. And again, you will hear me talking a few times, like JWST will help us there. And this is one of the problems, of course, which JWST is designed for, to really find and characterize the galaxy population at redshift 10 and above. Now, these models, these very simple models, are also able to reproduce things such as the star formation rate main sequence, right? This relation between the star formation and the stellar mass. And this is very natural because it comes out from just having the accretion rate of a dark matter halo being also proportional to the mass. Interestingly, and this has been also very nicely shown by Aldo's work, that the scatter of the star forming sequence is very similar to the scatter in dark matter accretion rates at the given mass. And so this seems to also reproduce the scatter of the main sequence very well. And so then, of course, the question is, are we done and can we go out to the vine? And the answer is no, of course not. The physics, of course, that shapes the star formation efficiency is something that I haven't really discussed. And also what is responsible then at the very massive end for the quenching is something I have not touched upon. And again, we have some ideas from simple toy model calculations, even more sophisticated modeling, that maybe at low masses, solar feedback leads to suppression of star formation, and at high mass it might be black hole feedback. And then there are many other physical processes that are, of course, related to stellar and black hole feedback that also can shape the star formation efficiency. So how can we make further progress? Well, one way to do this is to go to more complex models, right? So we can go, for example, to numerical simulations. And so what I show you here is a beautiful movie by the illustrious TNG simulation team. This is TNG 50, and I think it's very, very hard to see. But what you can see here is the gas accretion onto the galaxy. This is redshift up here. This is the solar component. This is the large-scale dark matter distribution of this system. And so in these models, there are recipes now for star formation, for stellar feedback, for black hole feedback, and they're all solved numerically in the computer. And you can see that they look beautiful, and they nowadays are also able to reproduce the redshift universe, the redshift 0 universe very well. And again, these are not perfect models. From a physical perspective, we try really to implement all the physics we think is important, but it's obvious that you cannot resolve the scales of an individual stars and large-scale structure at the same time. And so you always have to go to some kind of subgrid models in these models as well. So you have some kind of an approximation there. So I have been working more on cosmological zoom-in simulations, in particular the VILA simulation. This is a simulation suite of 35 halos, where we focus particularly on redshift 1 objects and above. So these simulations have solar feedback, radiation feedback from stars, but they don't have any black hole feedback. And so one cannot really look into the quenching of star formation in those objects, we think. So what did we learn from these simulations? Well, the first thing is to look into how galaxies actually evolve relative to the star forming sequence as a function of mass or redshift or time, right? So this is basically time for an individual object. And what we find is that galaxies are not always at the same distance, they're not always above or below the star-forming main sequence, but they actually oscillate, they self-regulate about the star-forming main sequence. And so these galaxies at early times, in particular at redshift 4, 5, and so on, they are very gas-rich. So they have gas fractions of 50% or so. And although they have some rotation, they are very easy to be disturbed. So you can think here that the galaxy is slowly rotating, but then with a counter-rotating stream or even a minor merger comes in that is counter-rotating, that can be enough to basically lower the angular momentum of the whole gas disk, which leads then to a lot of gas falling into the core. While this happens, we call this compaction. When this happens, you see that now the gas surface density in the core, shoots up by nearly an order of magnitude, and this leads to much more star formation, right, to a nuclear starburst. The galaxy moves up relative to the rest of the population, is now at the upper envelope of the main sequence. And you can also see that on spatial resolved scales, the specific star formation profile is now increasing to the central region. And so what you're finding is that you're forming these very dense centers, you're forming a bulge-like component. Now, because the gas gets consumed into stars and the stars also blow out gas, this leads actually to a suppression of star formation. Now, the galaxy says, I want to quench, I want to move away, I want to go below the star forming main sequence. But what happens is that at these early times, the replenishment time of the gas disk is much shorter than the depletion time, So you're able to reaccrete gas, in particular in the outskirts. So you can see that the gas now sits in the outskirts. You have something like a ring-like structure, and the specific star formation profile is now increasing to the outside. And so you're forming most of the stars in kind of more in the outskirts here. And you can go through such evolutionary phases, up and down several times, before then you fully quench the star formation in a galaxy. So this is a model, right? And Arlo Shapley once said, no one trusts a model except the person who wrote it. Everyone trusts an observation except the person who made it. And I feel that this is actually very true. So let's move on to the observations. And one very easy comparison one can do with understanding whether galaxies really oscillate about the main sequence is looking at galaxies relative to the star forming main sequence and look at their gas fraction as well as depletion times. And there have been a lot of measurements, in particular by Rainer Genzel's group in Munich, to understand these scaling relations. And we see that we are able to reproduce these scaling relations very naturally with such a model. What are other ways to test these oscillations? And here I'm talking about temporally resolving galaxies. And this is actually going beyond just these evolutionary cycles about the main sequence. This is very general thinking about how is star formation regulated. So the idea here is that we have a wide range of different physical processes that act on different spatial scales, but they also work on different temporal scales. And so if you would be able to measure the star formation history, and particularly the variability or the burstiness of the star formation history, you should be able to decode these different processes from the star formation history. And we have been working a lot on this, more on the theoretical side, and move now slowly into the observational side with this idea. And unfortunately, I don't have time today to talk about this more, but if you're interested, I'm very happy to chat. So this is really motivated by the HA light curve community, where people study variability on yearly or monthly basis. But we think we can apply similar methodologies on longer time scales for galaxies as well. So the model before also predicted strong gradients of the specific star formation rate relative to the main sequence. And so this is what I want to look into now a little bit. How is the star formation actually distributed, and how is the morphology of the galaxies linked to the distance from the star forming main sequence? And so here we have been conducting the largest adaptive optics spatially solved spectroscopic survey with SYNFONY at the Very Large Telescope in Chile. And I've been leading the Hubble Space Telescope follow-up of this survey. And so we have, taken images such as those. It's maybe hard to see. You can see the IoA guiding stars, and then you can see the beautiful, galaxy. This is a galaxy at redshift of 2. And so this is a color composite BIH. So this is rest frame far UV, near UV, and rest frame optical light. So this is a galaxy at redshift 2. And now with the Very Large Telescope, with SYNFONY, we were able to map out the H-alpha luminosity, as well as the H-alpha kinematics. And so it's, I think, pretty cool, right? I mean, we are detecting now photons that traveled for 10 billion years, and now we can start observing them on spatially solved scales. Again, thanks to adaptive optics, we can study basically the maps between, HST and ground-based, on the same kiloparsec scale. Now, I will not be talking about, kinematics of these galaxies, but Hanna Ugler has done a lot of work on these kind of data to analyze the velocity maps. So you should talk with her if you haven't done so yet. Okay, distribution of star formation. So what I show you here now is, stellar mass. This is for rather massive galaxies in our sample now. So the stellar mass density is a function of radius. This is from Hubble. And then I show you in blue the star formation rate surface density coming in from SYNFONY. And what you can see is that when you look at the stellar mass distribution, these galaxies are well reproduced by a stochastic index of 3 profiles, and they are rather concentrated. They have a very high central density in the core, a few times 10 to the 10 solar masses per kiloparsec squared. So this is very comparable to local, early type galaxies. But their star formation is much more, something like an exponential profile. And so what we find is that it seems that these galaxies have already bulges present in their cores. And so if you now look at the specific star formation profile to understand how these galaxies are actually growing in relative terms, we see that the lower mass galaxies in our sample, they have roughly flat specific star formation profiles. So they're growing roughly self-similarly with time. But the more massive galaxies in our sample, they have this decrease in the specific star formation to the core. And this is, when you look at the mass stopping time scale, this is longer than the Hubble time, which implies that these galaxies have very little star formation in the core relative to the mass that is already present. And so we put forward this discovery that basically these galaxies have very dense cores and they're quenching from the inside out. They're reducing their star formation from the inside out and forming then typical M-star early type galaxies at redshift 0. Okay. So now let's look into how these profiles of specific star formations, well, what I want to maybe mention here is that if you squeeze your eye, you can see there are individual lines for individual objects. Okay, and so there is this interesting trend, that we can try to figure out now whether galaxies above and below the star forming main sequence actually show the different gradients. And so this is, I think, what we would expect. So this is specific star formation with gradient. So this is the center versus the outskirts as a function of the distance from the main sequence. And so this is from the simulations, right? Galaxies above the main sequence seem to have, bulge formation. They have an increased specific star formation into the core. Whereas galaxies below the star forming main sequence, they mostly form their stars in the outskirts. So now I'm plotting the observations on top. We have only 10 objects where I would say we trust the spatially resolved star formation. And you can see it's kind of all over the place a little bit. There's maybe a bit of a trend, but I would say it's still early days to call. Now, recently with ALMA, there has been also a lot of very nice measurements tried to actually measure, in particular for these galaxies above the star forming main sequence, the dusk obscured star formation. And so those have shown that typically when you look at ALMA data in the dusk continuum, you can see that those are typically much smaller in size than when you look at the H band. So this implies that indeed there seems to be, dusty, small cores star formation going on in these galaxies. So again, I think that with JWST, it will help to nail this down just because we will have much better star formation with indicators that are less sensitive to dust obscuration. So let me move now and try to ask the question, well, okay, let's focus on this last phase of galaxies, when they want to quench their star formation. Okay. And so an interesting question is, of course, how quickly do galaxies transition from being star forming on the main sequence and being added to the quiescent sequence? How quickly do they switch off their star formation? Because this should be linked to the physics of quenching, right? If you blow out the gas, you would expect immediately to quench. If you starve a galaxy, you would have some star formation for some more time. And so how does this look now if you look at star forming galaxies? And this is what I would call the forward approach. You're observing galaxies that are just quenching now. Okay, now as you can imagine, this is difficult to really know what is the future of such a galaxy, right? It could be that they move again up, but we can make arguments that when they are very massive, they need to quench their star formation rather soon because they are so massive they cannot overshoot the mass function at redshift 0. And so what I show you here now is a very simple model where we say, okay, let's assume we have the measured stellar mass density profile at redshift 2, and we have also the star formation rate, and we are just integrating up and compare this to the redshift 0 stellar mass density profile of typical early type galaxies. And so what you see already from this image is that, yeah, well, in the core, there's a lot of stellar mass already made. We cannot keep forming stars for much longer. Otherwise, you would overproduce the stellar mass density that you observe in typical early type galaxies at redshift 0. And so if you're integrating this up, you can now compute how long can you still keep forming stars without violating redshift 0 constraints. And if you do this, you see that you can infer what we call a quenching timescale of a few hundred million years in the core, but you can keep forming stars for another 2-3 gigayears in the outskirts. Now, I think there's a very strong limitation with this because we know that minor mergers might play a role in mass accretion in the outskirts of some of these quiescent galaxies. And so you should take this more as an upper limit. But it's still an interesting question to understand now, okay, we see this inside-out quenching. What physics could it be explained by? And this is not very straightforward because many different physical processes could lead to a very similar input. Interestingly, if we look at the gas kinematics of these galaxies, we can find that only the most massive systems and only in their cores, they show very broadened H alpha features. Okay, when you do a decomposition of the H alpha line, you can see there's a narrow component and a broad component. And this broad component is very prominent only in the core of the most massive galaxies. And so we find an indication that there are powerful nuclear outflows in these galaxies that are possibly powered by black holes. On the theory side, we have done some work here with Eric and Nelson to study the specific star formation profiles in these galaxies. And at least in illustrious TNG, in that simulation, it's clear that you only get inside-out quenching if you include black hole feedback. So we were able to switch on and switch off black hole feedback and study whether you need this in order to explain inside-out quenching. And you only get inside-out quenching once you switch on the black hole feedback. But there are also other models, in particular the VLA simulations I've been looking at, that we can see very similar signatures of inside-out quenching without any HEN feedback. And so I would say the jury is still out also on this. There's of course the other way, right? If you say, well, Sandro, I'm not very sure if these galaxies really quench. Well, we can actually look at quiescent systems, and by age dating the stellar populations, we can go back in time, right? And we can try to reconstruct the star formation history and see how quickly they actually quench their star formation. Now, the problem is that when you look at the quiescent system, you're not really sure whether all the stars will be formed in that one system, or whether it's actually from other smaller systems, and then you have a merger, and so it's a combined stellar population. And so in order to circumvent this problem, what you want to do is you want to go as close to the epoch of quenching as possible. And this means, again, you want to go to earlier cosmic times. And so we have been conducting the Halo 7D survey. This is a survey with people who actually study the Milky Way halo. So these are people who are interested in these foreground stars, but they had many fillers, and we were putting in objects which are actually in the background. And so we got very deep spectroscopic data with DMOS at Keck that are 8 to 32 hours deep in integration, and to really probe the stellar populations of some of these redshift 1 galaxies. And so, just very briefly, the sample here is not a mass complete sample in any way, but the data quality is very similar to Legacy. It is, focusing mostly on quiescent galaxies and has a few galaxies at the massive end. So I have been very interested to understand now what can we learn from this spectra and this photometry. And I've been using ProSpectra, which is a Bayesian SED fitting code. And it allows you, because it has a spectroscopic calibration model, it allows you to combine the spectroscopic and the photometric data, rigorously, basically. And again, there is a wide range of different model parameters, and I don't have time to go into the details there, but we model 20 to 30 parameters. And I think some of the most important ones for us now in particular are the flexible dust attenuation model, as well as star formation histories that are non-parametric, meaning that they are flexible, so we can quench the star formation quickly or slowly, and so on. So how does this, priors are very important, happy to talk more about this. So how does this look? Okay, so this is showing you now one of the galaxies here. They're still pretty, but they look a bit more boring when you look at the HST images. You see here the photometry going all from the UV to the IRAC bands to the NIMS 24 emission. And then down here, this is where we have the spectrum, right? So it's a rather, it's in the optical range, right? And you can see all these absorption features. And so we are modeling all of this in a Bayesian way, so you can then get all the degeneracies and the covariances in the parameters. And so we are getting out are things like those. These are the star formation histories. So you can see that this galaxy increases star formation and then it decreases and quenches star formation. Now, why is it important to include both spectroscopy and photometry? Well, as it's important because the UV itself contains a lot of information about the attenuation, but also about the intermediate stellar populations. Right, so I show you here the light-weighted age that the typical certain wavelength traces, and you can see that the ultraviolet really contains age information going all from a few times 10 to the 6 all up to about 10 to the 9. So you want to include this in your fit as well. And it's important to have a flexible attenuation law because you want to make sure you marginalize over the uncertainty of the dust. And so what are kind of the key constraints you're getting out? Well, I'll show you here the quenching timescale. So this is how quickly the star formation drops as a function of the redshift of quenching. So this is the epoch when the galaxy actually quenches its star formation. And you can see that actually galaxies show a large diversity, right? So we have both galaxies that quench very rapidly and galaxies that quench very slowly. But we also have galaxies that quenched very recently, but also galaxies that quenched a long time ago. And so this is consistent with some other works that has been shown, in particular also by Francesco here, that shows that there's a wide range of different quenching pathways, actually. What we also did is we took the illustrious TNG simulation and projected it into the observational space, meaning we have mocked up the spectroscopy and the photometry and the read on our fitting. And you can see that overall, yes, we are in the ballpark, where the observations are, But you can see that we are missing some of the outlier population growth. We're missing some of the very slowly quenching galaxies. And in particular, we're missing the very early forming galaxies. And of course, these early forming galaxies, these early quenching galaxies are very interesting because again, the James Webb Space Telescope will be able to trace those and also characterize the populations of those galaxies in detail. So let me move now to JWST and kind of more the high redshift universe in the last few minutes. Okay, so with Hubble, of course, we have learned a lot about these galaxies as well, right? Identifying these objects is very challenging. The main method that we have been using is understanding that, yes, because of the high neutral fraction in the galactic medium above redshift 6, we can then identify quite easily these what we call dropouts. And so the idea is that you look at these, at these wavelengths shorter of the break and see that there is no galaxy there, and then you only see galaxy, or emission basically longwards of it. So we have recently been again going through the Hubble archive and the Spitzer archive, and Spitzer is very important because the break that you measure here can also be mimicked by a passive system at lower redshift. And so you want to include the IRAC bands from Spitzer in order to make sure that this galaxy is really a high redshift target. And so we found 11 candidate galaxies that are above redshift 9, and we have spectroscopic confirmation for 3 out of them. So again, I've been using Prospector then to understand what the populations of these galaxies are. So this is the same tool I mentioned to you before that we can use for quiescent galaxies at lower redshift. And so here again, I think the strength is that we can try to understand how the different priors in the star formation history manifest themselves in the posteriors. So what do I mean with this? Well, you see these galaxies are at high redshifts. There are very few data points that we can fit. And so it's very important that we understand what are the implications of our assumptions that we put in this modeling. And important is that the different star formation priors are actually all able to fit the observational data equally well. So the data at the moment doesn't prefer any of the priors. And the resulting fits for the star formations and stellar masses actually are quite similar, despite different priors. You can see here the star formation stellar masses. It's interesting that we find some very massive systems at these times already. And we also see something like a star forming main sequence, right? More massive galaxies typically have higher star formation rates. If you want to understand the star formation history, so how quickly these galaxies build up their star formation, it's a bit more difficult. You can see that some galaxies, well, maybe first, what is the figure? So this is the fraction of mass formed, as a function of lookback time. So you can see how galaxies are building up their stellar mass, and each panel shows an individual galaxy. You can see that here, this galaxy, for example, all the priors agree that this galaxy formed rather early, right? This is very interesting. It seems like there's a lot of star formation at early times. But for several other objects, it is actually very prior dependent, right? We can see that the bursty continuity prior, so a bursty prior prefers typically younger ages, whereas a continuity prior that assumes something like a constant star formation rate, typically infers other older ages. And so you can see that here in these cases, the data is not very informative. So if you now assume that the galaxies we have is representative of the cosmic volume, you can actually use this to understand how the cosmic star formation rate density looked like at earlier times, right? You're just extrapolating back in time. What you're seeing here is now the cosmic star formation density is stacked for all the galaxies in our sample. And you can see that when you assume a bursty or the parametric prior, you can see that we are consistent with this dotted line. This dotted line is for this very steep decrease in the cosmic star formation density I showed you before. On the other hand, if you assume a continuity prior or something that is like something like a Dirichlet prior, you can see that we are consistent with this dashed line, which is a much flatter evolution of the cosmic star formation rate density. So I would say the jury is still out whether we are either side here. Okay, so I think this is very interesting because JWST will help with understanding how much mass has formed already above redshift 15 and before. And I think here again I want to highlight Nicolas' work, right? He has done a lot of very nice work on these questions as well. So how can we do better actually with JWST, right? So what I show you here are the posteriors for the different spectra that we are getting out. And you can see the degeneracy that we get at the moment is not in the UV, right? The UV is there where we have the observations. That's where all these spectra through these different priors actually agree. But where we see the differences is actually with the strength of the break, of the 4,000 angstrom break, and the emission lines, right? This is where we have the degeneracy at the moment. And so what we want are either medium bands, right? From JWST that will help with, finding the continuum and emission lines, or of course spectra. And so we have a program particularly devoted to the ultra deep field, Hubble ultra deep field, to get the H alpha emission and emission lines generally for these objects. Okay, I have mentioned JWST a few times, and I don't think it needs introduction really, right? So I myself am part of the NIRCam instrument team, and JWST itself is of course very cool, right? Because it has a large mirror, and its wavelength sensitivity extends much beyond Hubble into the near infrared. And so on the NIRCam side, with the imaging, we will go from images currently with Spitzer at a few micron to images such as those. And this will help, of course, with finding very faint objects that are really far away. And another important crucial component is, of course, the spectroscopy. So we'll also be able to characterize these galaxies in much greater detail. And so again, this helps with finding the very first luminous structures, but I'm also very interested to understand, what is the galaxy population actually, during the epoch of ionization. And so I'm particularly involved in JADES. JADES stands for the JWST Advanced Deep Extragalactic Survey. So this is a large program where both NIRCam and NIRSpec, the science teams, came together, and we put together an 800-hour survey that we put in good north and good south for the next 3 years, right? 2002, 2003 is the current schedule. And the survey really provides images and spectra for, thousands of galaxies between redshift 2 and 10. And so it's really a unique survey, and it's the largest survey that is currently planned in the first 1 or 2 cycles. I just give you here, some numbers, right? So we have a deep part of the program with roughly 50 arc minutes squared, which is 10 sigma depths going up down to 30th magnitude. And the crucial part of this survey is that we can do the imaging first, so we can find the interesting targets, and then we can use NIRSpec to follow them up spectroscopically. And so I think that's how we have this very unique synergy between the NIRCam team and the NIRSpec team. And again, Roberto Malino here, of course, is one of the leaders of the NIRSpec team. So we have a very good collaboration there. And again, what are the key science questions that I'm particularly interested in? I just mentioned them here again, and you have heard them mention me before them. Basically, when do really the first galaxies form and the dark ages end? What are the populations of these first galaxies? Which galaxies or sources unionize the universe? When did the first galaxies cease their star formation? Also, how did bulge and disk components in galaxies form? And so what my current involvement here is that I'm currently co-leading the data reduction, the mosaic construction, the source detection, photometry part. So I've been generating a lot of mock observations and reducing that. And so we have been heavily working over this over the last 3 years. And so we're very excited now that we get real data. And we're also building a new photometry tool, a GPU-based photometry tool that allows you to forward model all the individual exposures so that you don't have to work with mosaics, because with mosaics, you always have the problem of correlated noise. And so this is something that we have been working heavily on in the last few months as well. Beside this, I still put on my theory hat, of course, from time to time. And here, there's been a lot of efforts, in particular by Rahul Khan and Aaron Smith and Enrico Baraldi, to use illustrious TNG simulations and move them forward into the epoch of ionization to also model the reionization process. And I'm particularly interested in the Thiessen zoom simulation part there, because there we will be able to get a model that self-consistently models beside the galaxy formation, also radiation, dust, and molecular chemistry. And we have been working a lot on getting radiation, in particular, modeling the Lyman alpha as well as the H alpha emission line profiles correctly. And so this is something that I'm happy to talk with you if you're interested about talking about that. Okay, I think this brings me to the end of my talk. So I know I went quite quickly, as usually, and then also talked about several different things. So let me quickly go through the main conclusion points. So first of all, I discussed with you a little bit the regulation of star formation, right? And the question there is, how do galaxies actually move about the star forming sequence? And I showed you that there is a tight correlation also with how galaxies are building up their morphology. I discussed with you that we already observe by redshift 2 mature galaxies, meaning that we see galaxies with massive bulges in the core. I presented to you the idea that temporally resolving galaxies is something very interesting to understand the internal workings of galaxies. And this is in particular interesting when we are not able to spatially resolve the galaxies, right? If you want to understand GMC physics, we can of course look at the local neighborhood. But we are having a hard time to understand GMC physics in the first galaxies. And by understanding the variability of star formation, we hope that we can decode, things that are beyond the spatially resolved scales, basically. I showed you that there are many different pathways to quiescence. It seems to be very diverse, which seems, to reflect that there might be internal and external quenching processes at work. And I also showed you that current observational data have a hard time to really constrain the epoch of the first galaxies. And this is something where, with JWST, we will really learn a lot. So, okay, thank you very much for your attention. I'm very happy to answer any question. Yeah, thanks.